Diffraction of light at a single slit. This is an arrangement for diffraction of light at a single slit. Here S is a monochromatic source of light. L1 is a lens which is used to send the parallel plane wavefront over the slit AB of width A. Let these rays meet at point C on the screen XY. If we consider that this screen is at a distance D from the slit, right? Now since the wavefront is incident over it, okay, and for the equidistance point from this slit the rays reach at point C, so the C corresponds to the position of central maximum. Now since this slit can sense the rays in all the direction, as we have already explained, if this is the aperture and rays are made to fall over it, they can get deviated from its path like this. So it means this portion will considered as the secondary wavelets which will reach at this point, means these can interfere with each other. Similarly, all portion of rays which are coming from this portion also interfere from each other and corresponds to the position of secondary minimas and maximum, and those which are reaching at equal distance from the point, these correspond to the position of central maximum. So here for the convenience sake we are considering this ray. Okay, first this is the central position of central maximum. Now let this deviated ray made to fall on the screen at point P1. Okay, and similarly all the portions of this slit will be sending disturbance and that will meet at point P1. Now at point P1 the intensity will be maximum or minimum depending upon the path difference between these two waves. For this we draw a perpendicular AN over this ray. Okay, so in this case we can say that the path difference, this ray should be almost straight, less deviated and straight. So the path difference between these two rays will be given by this AP minus BP, right? So we can say this BN. This BN is the path difference, and what its value should be. Now since this is the perpendicular and second angle is at this point, so this line this AN becomes the base. This BN is perpendicular and AB is hypotenuse. So perpendicular upon hypotenuse, that is BN upon AB, will be equal to sine theta. So BN is equal to AB sine theta. AB is what? This is A, which is equal to sine theta. So it means the path difference is equal to A sine theta. Now this path difference is equal to what value will decide whether here point P1 corresponds to the position of secondary minima or maxima. It is observed that when the source from monochromatic light is made to pass through the slit, we obtain a pattern like that. A maximum, and then the intensity of maximum and minimum goes on decreasing. Now let us discuss what are the positions for the secondaries minimas and secondary maxima. Now let's just consider first point, the position of secondary minimum. First is position of secondary minimum. Okay, it is observed that, now we know that minimum means destructive interference. Destructive interference means when crust fall over the trough, okay, or trough fall over the crust. So accordingly we can get the position of secondary minimum. So it is found that when the path difference A sine theta is equal to lambda, okay, in that case this position corresponds to the position of first secondary minimum. Let us understand how. For this we will consider that this slit AB is divided into equal parts. So the wavelets which are reaching from point A, and let this is the point O, okay, point A to point O, suppose that wavelets is having the path difference lambda by 2, and similarly point O and point B wavelets are having the path difference lambda by 2, so they will interfere and the resultant intensity at P1 is 0. Now to understand it diagrammatically, let us consider, basically we know that one wavelength means this one wavelength is this, okay. Now destructive interference will obtain when the crest of one wave overlap over the another wave, right? So now let us consider the wavelets which are reaching point P1 are such that the path difference between them is, suppose this lambda by 2, okay. Suppose from A and from O the wave reaches like this, and the path difference is lambda by 2, and similarly the wavelets reaching from D and C is having path difference half lambda by 2, that is equal to lambda by 2. So when means if I draw it more clearly, let this is from A to A, and from O to and B the path difference obtained is lambda by 2 in this direction. So in that case, when both these wavelets, this one and this one, when reaches at point P1, in that case they will interfere and overlap each other. In that case we will be having resultant intensity minimum. So we can say that destructive interference takes place. Similarly, when path difference between two waves reaching from A and B is 2 lambda, means when A sin theta is equal to 2 lambda, it means we can consider that this wavelets be divided into two equal parts such that lambda and lambda, for that we can consider that this A, O and OB, lambda path difference from these two wavelets and lambda path difference between two wavelets, so superimpose upon each other, and hence we obtain the resultant minimum intensity. So if we generalize, we can say that if the path difference is equal to n lambda, we will obtain the position of minimum intensity, and hence we can say we are having the destructive interference, right? Similarly, we can understand the concept of constructive interference or the position of the secondary maximums. Position